Hello everyone and welcome. I am Yudi. In this presentation, Junhan and I are going to introduce our work, refactoring the FreeBSD kernel with Check-C. As we all know, the C language is an unsafe programming language, as it lacks memory safety. For example, it does not check whether a pointer dereference is in bounds. If we have a sequence of memory like this, what if we modify the value of A4 and A5? The answer is, the password will be modified, and the program is jumped to an alternative address. Hackers can utilize this and perform a buffer overflow attack. If a buffer overflow attack is performed on an operating system kernel written in C, it will be more dangerous as the attacker can gain access to kernel mode. Microsoft has developed a dialect of C. Its name is Check-C. Check-C introduces spatial memory safety to the C language. It is fully compatible with existing C code, and it allows incrementally changing C code into spatially safe Check-C code. This could solve spatial memory safety problem without a complete rewrite to the kernel. Hence, we are attempting to use this new language as an experiment to modify part of the FreeBSD kernel with Check-C and reflects on whether this would be a good idea to do so. Check-C introduces new pointer types. PTRT is a checked pointer with type T, and array PTRT is a checked array pointer with type T. Note that a bound must be specified for array pointers so that compiler will perform array dereference checks. These new pointer types are incompatible with legacy C pointers. They can neither be directly assigned from legacy C codes and require conversion. Check-C allows conveniently modify the function arguments with the bound-safe interface to allow checked and unchecked code to interoperate by accepting polymorphic pointer types in function arguments. It also introduces a new type of code block, checked region. Within the checked region, use of legacy C pointers are strictly disallowed, and spatially safety within the region is guaranteed. Code outside checked region only guarantees memory safety on checked pointers. Our work mainly focuses on system calls and the network stack. They are part of the EOS kernel, which accepts external data, one from the user space and the other from the internet. Attackers can use malicious input on them and trigger an attack. We also have to modify the kernel support routine first. We first refactored a set of kernel support functions. This includes kernel copying functions, including memset, memmove, and memcopy. We also refactored malloc and free. Although Check-C also modifies them for user applications, we need to modify the kernel version of malloc and free, which are maintained by the FreeBSD kernel. These functions now deal with and could return checked pointers. The variants of copy in and copy out are also refactored. Copy in copies a block of memory from the application memory to the kernel memory, and copy out does the opposite. This is one set of the most crucial functions, as they act as guardians between the user space and kernel space. They do not check internally on the kernel data buffer. We can modify the function declaration with bound-safe interfaces to ensure that no buffer overread and buffer override is possible on the kernel data buffers. Next, functions that call copy in and copy out are modified. Pointers to strings and arrays are replaced with check pointers in those functions. The TCP IP stack is a large module, and we cannot refactor it completely. Hence, we chose the mbuf packet, IP and UDP processing code to refactor. mbuf is the underlying buffer data structure for network packets, and it performs operations such as prepending and removing packet headers. IP input and IP output appends and processes IP headers, while UDP input and UDP output appends and processes UDP headers. Most of my work can be done by switching legacy pointers to checked pointers and by adding bound-safe interfaces. The challenge here is that the mbuf packet does pointer arithmetics, and some of them cannot be easily refactored to Check-C, as Check-C adds restrictions on pointer arithmetics for them to be spatially safe. We still managed to refactor most mbuf manipulating functions and put them within checked regions. However, there are a few functions that cannot be modified and secured because due to the restriction on pointer arithmetics. This can only be solved if we completely rewrite the mbuf packet, which is unnecessary, and they directly disobeys our attempt to refactor without doing too much modification. Therefore, I left them as they were unchecked. In addition, a few functions are not included in the checked region since they call functions and macros outside our scope of refactor. They could be spatially safe if we start to modify more parts of the kernel. CheckC has its own advantage for its compatibility with C and its modularity to allow incremental modification. This is the main reason we chose CheckC over other languages for this job. CheckC is fully compatible with C, and its compiler is a direct modification of the Clang compiler. The original FreeBSD 12 compiler can be compiled directly with the checked Clang, just like it can be compiled with regular Clang. We can directly make changes on the kernel code to use check pointers, bound-safe interfaces, and check regions. We can use check pointers along with legacy pointers if we only want to put certain pointers to be spatially safe. We can also incrementally put codes in checked region to ensure that more pieces of code are safe. However, as a developing language, there are still quite a few problems with both the language itself and its compiler. First, the language lacks support for inferring equivalent expressions. This means that bounds checking cannot always prove for bound equality. For example, check Clang does not know that p plus x minus x equals to p. Instead, the compiler generates a warning or an error in the kernel. In this case, we have to manually insert code to do such bound checking. This adds additional work during refactoring and makes the code messier with lots of manually inserted dynamic checks. In my opinion, it would be nice if the compiler could insert automatically dynamic checks for us, or if it could have a set solver to prove such equalities. Second, kernels use a wide range of macros. They do not support bound-safe interfaces. Hence, in order to use macros for check pointers, we need to create a separate macro. This brings inconvenience when it comes to modify and maintain two macros instead of one. When we have to maintain a set of very long and convoluted macros, it will introduce possibilities for human error. And now, Junhan will present the evaluation part.
Thank you, Yudi. I will now present our evaluation of the FreeBSD kernel. Speaking of the evaluation part, we divide it into three parts. We first evaluate the efforts of refactorization, and then we evaluate the performance overhead. Lastly, we will evaluate the code size overhead. We use getDiff to measure the lines of code changed during the refactorization, and we found that we delete around 500 to 600 lines of code and added 1,700 lines of source code. Our modification of FreeBSD kernel was across 61 files, including the system calls like read, write, send, and receive, and mbuf structures, as well as the UDP functions. We also did time measurement for this project. Yudi and I are two undergraduate students, and we spent around 7 to 8 hours a week in total on this project, and the project lasts 3 months. The total time spent on this project is more than 100 hours, and since we had no experience use CheckC before this project, a more experienced programmer or programmers who are more familiar with CheckC could spend less time refactoring the kernel with CheckC. We divided the performance evaluation parts into two parts, system calls and UDP. Since we modify both parts, we use LMBench to test system calls overhead, and we test several subsystems including file system, get PPID system call, pipe and Unix socket bandwidth and latency. We also test read, write, send, receive system calls, which use copy in and copy out functions. We also test open system call for copying string function. Here's a graph of the latency evaluation showing the average of latency of each system. The orange bar is the latency of checked FreeBSD, and the blue bar is the original one, which is the baseline. As we can see here, there's almost no latency overhead, and some of the data from checked FreeBSD is actually even better than the original one. This is because of noise during the measurement. If we plus and minus the standard deviation to each data, we will find the data is identical. So there should be very less or even no overhead at all. The same result is also for the bandwidth. As shown in the graph, checked FreeBSD kernel makes almost no overhead, and according to the checkc official document, we found that the checkc compiler can optimize some checks away, and sometimes the compiler may judge that it is trivial to do such checks, so it just optimizing them away. When measuring the network, which is the UDP performance actually, we use two tools. We use LM-Bench and IPERF3. We use LM-Bench to measure the UDP latency. To be more specific, the UDP4 latency, because LM-Bench does not support UDP6 latency or any of the UDP bandwidth test. We then use IPERF3 to set up a server client, sending data from the client to the server and measure the UDP bandwidth from the server side. This is the UDP latency graph. And this is the UDP bandwidth graph. As shown in both graphs, we can say that the checked FreeBSD kernel does not provide extra overhead while using the checked secure code to do UDP packet manipulation. And this is expected since we only refactor the code that processes UDP and IP headers, and they should only be used once per packet when UDP packet is sent or received. After we compile the kernel, we found that the kernel after factorization is actually 504 bytes smaller than the baseline. And we disassembled some functions and found that the checkc compiler makes different instruction selection when compiling the code containing checkc code. And this might sometimes lead the compiler to generate smaller code. And for the details, we included our observation in the paper for further discussion. In conclusion, we use checkc and its bounded pointer to refactor the copy in and copy out function and copy in string function actually, and some of the usage in FreeBSD kernel. We also refactored the mbuf structure and the UDP subsystem UDP functions in the FreeBSD kernel. As a result, we can guarantee spatial memory safety in some copy in and copy out usage and packet manipulation in UDP and IP. According to the evaluation data, there is partially no performance overhead in these subsystems. We don't know whether refactoring the whole kernel with checkc will lead to more observable overhead, but right now, the checkc is showing a very good performance for refactored kernel. Lastly, this project is done by 2 undergraduate students, Yudi and I. We spent more than 100 hours to get this project done, and this project lasts 3 months. We believe more experienced programmers are able to use checkc more efficiently. As a result, refactoring C written insecure program with checkc, right now it is a very good approach, and we are eager to see both improvement of checkc itself and people using checkc to improve more programs to make it safer from buffer overflow and buffer overread attacks. Thank you.